Hi guys. So today we're going to look at systems of inequalities. So what we're going to do is, instead of finding one specific solution like we did with other systems, where we were finding that one place where these lines intersected or where the planes intersected, instead what we're going to look at now is a region where this system is actually going to be true. So it's not just going to be one specific point. So this graph is actually going to give us our solution because it's going to show us all of the possible values. So starting with this first one, we're looking at where y is greater than negative 2x minus 5. So I'm going to start by graphing that inequality. Since it's negative 2x minus 5, I have a y-intercept of negative 5, slope of negative 2. And because it was greater than and not greater than or equal to, it's going to be a dotted line. All right, I'm going to wait on my shading actually until I finished graphing my lines. Now I'm going to do x plus 3, so y-intercept of 3, slope of 1. And this time it's going to be a solid line. And then my last line, y is greater than x minus 2, so y-intercept of negative 2. Again, a slope of 1. And there's that line. So now what I'm going to do is I'm going to go ahead and do my shading. So for my blue line, I wanted to do everywhere where y was greater than negative 2x minus 5. So that's going to be everything above that line. So I'm going to go ahead and shade everything that's above that. Y is less than or equal to x plus 3. That's everything that's below that line. And then if I do y is greater than or equal to x minus 2, that's everything that's above my green line, which is everything here. So if you notice, it's a little bit messy here, so I'm going to go ahead and erase those. You can see there was one section where we shaded all three of those regions, and that's this part right here that I just made green. That was where all three of these areas where the shading met up. So this shaded area here, that's our feasible region for this problem. That's telling us all of the possible solutions to this system. So any point that falls within that shaded region or that falls on that solid line would be a solution to this system. So for example, 0, 0 would be a solution to this system. 0, 3 would be a solution to this system because it still falls on the solid line. Something that would not be a system, anything outside of that region. So for example, 2, negative 1. Okay, that would not be a solution because it falls outside of that shaded region. Anything that falls on the dotted line is also not part of it. So for example, negative 2, negative 1. Okay, negative 2, negative 1 would not be in the solution because it's on the dotted line. The reason that doesn't work as a solution, because if I plug it in to every single equation, every equation needs to give me a true statement. And if I were to plug negative 2 into this equation, then I would get negative 2 times negative 2 minus 5, which is negative 1. I would say that negative 1 is greater than negative 1, which is not a true statement because it's not or equal to. So again, it has to be true for every statement that's on there. So solid line is okay, dotted line is actually not part of that solution. All right, so go ahead and pause the video and try B. All right, so in order to graph B, I need to start by getting y by itself. So I've got 3y is less than negative 2x plus 6. So y is less than negative 2/3 x plus 2. Y-intercept of 2. Slope of negative 2/3, so down 2 over 3. This one is going to be a dotted or dashed line because it's just less than, it's not or equal to. All right, my second line, y is greater than or equal to negative 2/3 x plus 4. So same slope, but a different y-intercept. So there's that line. Then my last one, in order to graph it, again, I need to solve for y. So y is less than 2x minus 2. And this one would also be a dotted or dashed line. All right, and then I'll go ahead and do my shading. So I'm starting with where y is less than negative 2/3 x plus 2. I'm doing where y is greater than negative 2/3 x plus 4. And then I'm graphing where y is less than 2x minus 2. And if you notice, on this graph, there is not a single section where all of that shading meets up. So this graph actually has no solutions at all. There are no points that can make all three of those equations true equations. All right, so now we're just going to do the same thing but backwards. We're going to write the equation from the graphs. So what I like to do is just start one line at a time. So we'll start with this line here. I'm going to write the equation of that line. So that line has a slope of 1/2. It's got a y-intercept of -2. It's a dotted line, so I'm not going to be or equal to. And I have shaded above that line, so I'm going to do y is greater than. All right, then I'm going to look at my next one. That's got a slope of -1/2, a y-intercept of 1. I've shaded below that line. It's dotted, so it's going to be y is less than. And then I'm going to do my last one. It's this vertical line over here. Vertical lines would be x equals lines. I'm looking at x in relation to -3. And since I'm shaded to the right, all of the x values to the right of -3 are greater than. And since it's a solid, it's or equal. So that would be my system of equations for that graph. All right, so now doing B. So I'm going to, same thing, I'm going to write the equation of each line. We'll start with the solid line. That one has a slope of -1, y-intercept of 2, solid line that's shaded above. All right, look at line number 2. We'll go ahead and do this one. That one's got a slope of 3, y-intercept of 2, shaded below and not equal to. And then finally look at my last one, shaded above, not equal to, has a slope of 1/3 and a y-intercept of -1. That's the equation of all of those with the right shading, and that gives me my system. All right, so now we're going to go on and look at some applications, which is really kind of the big important part of this section. So we've got $60 to spend on toys. The stuffed animals cost $3. The cars cost $2. We want to buy more cars than stuffed animals, and you want to buy a minimum of 4 stuffed animals. So in order to graph this system of inequalities, we need to come up with what our equations actually are. So to start, the first thing you got to do in these word problems is define your variables. You're going to want to use x and y because we're going to be graphing several equations here. So I'm going to quantify something as x, and for x, I'm going to say number of stuffed animals. And then for y, I'm going to do number of cars. All right, so the first equation that I can write, if I'm spending $60 at the most, then it costs $3 for each animal, so I can do 3x plus 2y is less than or equal to 60. The other information that's given, it tells me that I want to buy more cars than stuffed animals, so cars are going to be greater than or equal, not or equal to in this case, I apologize. Y is greater than x. Then my last criteria, it tells me that I want to buy a minimum of 4 stuffed animals. So I want animals to be greater than or equal to 4. All right, so now we're going to go ahead and graph this. So I'm going to solve for y on this first equation. So 2y is less than or equal to -3x plus 60. So y is less than or equal to -3/2 x plus 30. All right, so in order to sketch these graphs, something we need to consider is the scale that we're going to use on these graphs to get a good picture. Now you can use whatever scale you want, whatever you think is going to make the most sense. So I'm just going to go ahead and use a scale of 2. So 2, 4, 6, 8. And 30 is actually going to be up there then as a result. Right, and then same thing on my y or x-axis. We'll do 2, 4, 6, 8. And then I'm going to go ahead and actually graph this line then. All right, so I'm going from 30 with a slope of -3/2. So there's my green line. And again, I'm going to wait on my shading. I've got y is greater than x, so I'm going to make my line. And then I've got x is greater than or equal to 4, so that's going to be a solid line. right there. So my shading, this time instead I'm going to do it in one step. So I'm going to shade somewhere to the right of that purple line. I'm going to shade above the blue line, and I'm going to shade below that green line. So you can see the only area where all three of those will be true is in this little triangle right there. So that triangle represents the solutions for this problem, and all the possible answers that could make sense for this problem. So we give 3 solutions. There's lots of different ones on here. I could do 6 animals and 8 cars, for example. I could do 10 animals and 12 cars. I could do 6 animals and 16 cars. Okay, so lots of different possibilities here. So then it's asking, would you be able to buy 9 cars and 12 stuffed animals? Now keep in mind, our animals is the x-axis. So I'm looking for 12, 9. And I'm trying to see if 12, 9 falls within that shaded region. And it does not. Okay, so no, that would not be a possibility. All right, so now what we're going to do is we're going to take this one step farther. We're going to go ahead and look at a linear programming question, which is really going to take the same concept we just did, but it's going to apply an additional equation to it so we can evaluate maximum and minimums within this problem. So this one here, this is an example of the steps that we're going to do for linear programming without actually getting into the word problem part of it. So when we get into an actual example here, we're going to write this statement, but for now we're just going to see how that statement can be used. So what we have, again, a system of inequalities that I'm going to go ahead and graph. X is greater than or equal to 0. Y is greater than or equal to 0. And then I'm also going to graph where y is less than or equal to negative x plus 6. And since it's less than that, I'm going to shade below. So that purple triangle is my feasible region here. So now what we're going to do from this feasible region, since we're looking at maximums and minimums, we're going to worry about the vertices of this feasible region. So my feasible region has vertices of 0, 0, 0, 6, and 6, 0. So then what we're going to do, once we have all of our vertices, we're going to take those vertices and plug them into this objective function. So that is a graph. Again, we are not graphing that point. We're using that function to evaluate these vertices. So what I'm going to do is I'm going to take, I'll do C for the first one. I'll do 0, 0. So if I take the vertices 0, 0, then my C would be 4 times 0 plus 5 times 0, which is just 0. So for the vertices 0, 0, my C value is 0. All right, then I try the vertices 0, 6. So 4 times 0 plus 5 times 6 gives me a C value of 30. And then the last vertex is 6, 0. 4 times 6, 24, plus 0 is 24. So now I've got 3 different possibilities here for C. Out of those possibilities, this is where I would answer my question. So I need to consider, is my question asking for minimum or maximum? Now in this case, we're just looking at both to kind of see what it does. But starting with the minimum, the lowest C value I have there is 0. That occurs at the vertice of 0, 0, so when x is 0 and y is 0. The maximum value here was 30. That happened when x was 0 and when y was 6. All right. So now we're going to do this whole thing, combine all this together to do a linear programming question. So again, the way these work, the steps were written in the box at the top of your notes, but they're also going to be rewritten within the problem. So we have a school that's trying to find a way to use their funds to hire teachers and aides. It tells you the average salary for teachers, the average salary for aides, and then it gives you a certain number of requirements. So those requirements are going to be what we use to write our equations for our constraints, which are going to be our inequalities. Then when we're done with all of that, we are finally going to determine the number of teachers and aides that would represent the minimum cost to the school district. So again, whenever we're solving these problems, the first thing we want to make sure we do is that we go ahead and identify what our variables are. All right, so my variable here, we'll let x stand for the number of aides, and and I'll let y stand for the number of teachers. All right, step 2, we're going to create our objective function. So this is going to be that c equals equation, and it's going to have an x and a y. This is the equation that really helps us answer the final question. So the final question is basically how many teachers and aides can we pay for the lowest amount of money. So we need to consider the number of teachers and aides versus their pay. So our objective function would be 20,000 x plus 30,000 y. Because the number of teachers times their salary plus the number of aides times their salary would give us the total amount of money that we're spending. All right, our constraints, those are going to be the inequalities based off of all of the specifics that it gave us. So to start, the building can accommodate no more than 50 faculty members. So x plus y has to be less than or equal to 50. Number 2, the school must have a minimum of 20 faculty members. So x plus y has to be greater than or equal to 20. All right, step 3, it says there must be at least 12 teachers, so y has to be greater than or equal to 12. Next one, it says the proper teacher to aide ratio, the number of teachers must be at least half the number of aides. So the number of teachers greater than or equal to half the number of aides. And then finally, there's one criteria that's not listed on there that's actually going to be very important. Now, we know our teachers, we have to have at least 12, but it doesn't give us any sort of a minimum on the number of aides. We can't have a negative number of aides. So we need to make sure that we consider that x has to be greater than or equal to 0. All right, so step 4, we're going to go over here and we're going to graph our feasible region. So we're going to go ahead and graph all these equations and we're going to find the area where all of these are shaded. So x is greater than or equal to 0. If I solve for y in that top equation, I would get y is less than or equal to negative x plus 50. So let me go ahead and label my graph here. So 50 would be up there. And then same thing, I'll count by 5s on the other side. All right, so if I'm doing y is less than negative x plus 50, that would be right here. All right, my graph in red, if I solve for y is less than or equal to negative x plus 20. So there's that graph. All right, we do the graph in purple. Y is greater than or equal to 12, so that's going to be a horizontal line at 12. I've got the green graph, 1/2 x, so from 0, 0 up 1 over 2. All right, and then again, we've already graphed our x is greater than or equal to 0. So then from here, I need to figure out what's my actual feasible region. What part here would I be shading? So first thing, I'm going to be shading below the blue line. So something in here. I'm going to be shading above the red line. So something in there. I'm going to be shading above the green. And I'm also going to be shading above the purple. So my feasible region is going to be everything in this region right here. So once I have this done, next step is to find my vertices. Now some of these are going to be very obvious, some of them are not. So right here, one of my vertices is 0, 50. All right, so another one over here, 0, 20. The other 3 vertices, though, depending on the scale of your graph, may be harder to find, and that's okay. We may need to solve for these algebraically. So if you consider the purple and the red line there, to find that intersection of those vertices, I'm just really finding the intersection of those lines. It doesn't matter that it's an inequality. I just need to know where do those lines intersect. So I'm really finding when 12 is equal to negative x plus 20. So that means that negative 8 equals negative x, so I get an x equals 8. So if x equals 8 at that point, I know that y equals 12 because that's the value that I plugged in. So 8, 12 is another vertice. All right, then I've got this vertice over here. Again, we know the y coordinate is 12 because the line is y equals 12. So I need to find the intersection. So I would do 12 equals the green line. The green line is 1/2 x. So x is equal to 24. So that means the coordinates of that vertice would be 24, 12. And then finally, this last one, again, I have to solve for this one algebraically. So I'm looking for where the blue and the green line intersect. So I am looking for where x plus y is equal to 1/2 x. And I'm looking at the wrong equation, well, the wrong form of the equation. So I am looking for where negative x plus 50 is equal to 1/2 x. So 50 is equal to 3 over 2x. So multiply by 2/3, so 100 over 3 is equal to x. Now in this case, I don't automatically know what the y-coordinate is. Down here on these two vertices, it was a little bit easier because I knew the y-coordinate was 12. But in this case, I find the intersection of two other lines. So once I know that x-coordinate, I have to take it and plug it back in to get that y-coordinate. So if I plug it back in, well, 1/2 times 100 over 3 is 50 over 3. So the coordinates of that last vertice would be 100 over 3, comma 50 over 3. So now I can see that I have 1, 2, 3, 4, 5 possible vertices here. So what I care about now is I care about which of these vertices is going to give me the lowest total cost for teachers and aides. So this is where the objective function comes in. So I'm going to take those vertices, plug them into that objective function, and determine which of these is going to give me the lowest value. So I'm going to go ahead and plug all those in. And then when I plug those in, 812 is actually going to give me my minimum value. So that minimum value ends up being, I believe it was 520,000. Let me check real quick. Yep, so 812, when I'm plugging that into the equation, that's going to give me 520,000, which is the smallest out of all those other vertices. Your maximum one would have been the 050. That would have given you a maximum of $1,500,000. But here, again, specifically look at what your question is asking for. The question is not even asking what the total cost is. It's saying determine the number of teachers and aides that would represent that minimum. So the number of teachers and aides would be 8 aides and 12 teachers. All right, so that's it for systems of inequalities.